Hey, so, show last night went pretty okay. Although I guess in the future, some of my videos are going to seem kind of weird, referencing shows and interviews and stuff that happened a while ago. Well, anyway, I guess that doesn't really matter. We're going to go ahead and talk about science, because science is dope. So, here we have some interesting stuff. Let me see. I actually have notes on this to make my life a little bit easier. So, what we're dealing with here, this multilingual circuit optomechanical transducer link, essentially what this would allow is like a transistor, transducer, what have you. A transistor, though, that could be run off of not just electricity, maybe light, sound. What are the other things here? Optical, acoustic, and radio waves, of which only electrical is the most heat-inducing. So this could allow for some real... it could really open up materials science in the realm of computing. Basically, you could transmit information instead of by electrical impulses, light, without having to use like a dedicated, say, fiber optic board. You know, you could use the same transistor for everything. Pretty wild. Diddly-dum. And also, you know, you could interface between really unlike interface types. So, potential for interconnectivity is astounding. So, that's our article 1. Links will be below. Next one. This is astounding stuff as well. Yeah. This one goes out to you, Biscuit. Yeah, buddy. Keep fighting. So anyway, the long and short of this guy is it reduces the cancer's ability to survive. It becomes less stable in and of itself, you know, by way of the treatment, and less able to resist further treatments, chemotherapy, radiological treatments, hell, I don't know, genealogical treatments for that matter. Just to read it off to you at the beginning here, researchers UC Davis, in collaboration with other institutions, found that suppressing the nuclear receptor protein RORY with small molecule compounds can reduce androgen receptor levels in castration-resistant prostate cancer and stop tumor growth. Which, that's a lot of big science-y words. But what this is saying is basically, you're giving the cancer a flu. It's just taking away its ability to be cancer. At least to the extent that cancer is as it is. So, to be added to a, shall we say, repertoire of treatments, this could increase survivability rates, I don't know, by a score, orders of magnitudes even, possibly. This could even take us into the ways of, you know, completely eliminating such things. Neat stuff, right? I certainly think so. I've got, well, my mom and dad both have cancer, so it's something I'm really mindful of. So next up, this is some really cool cutting-edge stuff, too. So, antibiotics, mechanical antibiotic effects. Imagine that. So, let's see. Do we get a good picture here? Go away. Yeah. Let's get a good view here. So, somewhat akin to the foot of a gecko, or something else. You have stuff that is basically, how should we say, it is a microspikes. It basically just tears things apart on a microscopic level. So bacteria that gets on here is just ripped to shreds. Its cell walls are pierced and it can't maintain integrity. Stuff just falls apart. It's absolutely it is the way. Excuse me. Also, the pardon. This stuff, it can be made to make an area less prone to infection. I mean, you could coat, say, implants in this stuff and just straight put it into a body. You might not even have to treat an implant like artificial knee, what have you, or, you know, in the coming wave of brain implants, you're going to need things like this because an infection in the brain, well, that's the last thing you need. The last. But anyway, this stuff, it can be made of bioplastics from egg whites, soy, wheat, petrochemicals, and it's just astoundingly more effective than anything we've had up till now. I mean, this is a way to stand against that looming post-antibiotic future that we all face. So, there's 1, 2, 3. Let's go on to the next interesting thing. While we're doing medicine, here we go. Nanoparticles. Nanodrugs. They're specifically built to target cancerous tissue, and they allow the treatment to avoid excessive damage to the surrounding areas. What they use is cisplatin. I'll bring that up in Wikipedia here and give a brief explanation, but it is a horrendously toxic compound. Cisplatin, member of the class of platinum-containing anti-cancer drugs. Well, side effects. Here we go. Nephrotoxicity, major kidney damage, neurotoxic, nausea and vomiting, which is normal for any chemotherapy, ototoxicity, hearing loss. Hearing loss. This, again, neurotoxic. It is going to go directly after your nervous system. Now, and electrolytic disturbances, hypomagnesemia. I'm not familiar with any of these. Anywho. And a hemolytic anemia. Yeesh. So destroying your red cell membranes. Christ on a cracker. This vile stuff, it works. It works very well. But by way of this, you would basically be having the stuff and it would be going directly into the cancer cells. It wouldn't be intravenously administered. You could have massive doses, but those massive doses go directly into tumorous growths. And you can, you know, subvert the whole process and really make it work better. Alright, now have I got more? I think that's about all I've got on medicine for now. So, we're going to move on to materials science. One of my favorite areas of science. Of course, links to all this will be in the description box below. Now, graphene nanoribbons, perfect zigzagging edges. What this means is tape. Simple as that. Long, perfect strings. Cordage of graphene. Atoms thick. And with graphene's possibilities in use for electrical components, that's going to allow for that much smaller wiring surfaces, or to be used, well, anywhere you can use graphene. I mean, you could layer these graphene weaves. Well, suffice it to say, this goes beyond really anything I can properly discuss. There's just so many different things that can be done with graphene. It can conduct. It can build a space elevator, carry us to the damn future. And here is another interesting one. This is what stands to look to be the best possibility as far as taking us to space in the future. If you'll notice, it looks akin to basically connected versions of those. So a carbon nanotube, but made of graphene. And there are many and varied ideas, principles, forms, like the buckyball, for instance, sheet graphene, graphene ribbon now, precision nanoconstruction such as this for nanotubes. So the trouble with building nano stuff is the machinery to build it on its size. So this is an article on constructing things. I'll just read you off the two here because it'll help to elucidate the point. As reported online the week of March 28th in the journal Proceedings of the National Academy of Sciences, researchers at the U.S. DOE Lawrence Berkeley National Lab have discovered a family of nature-inspired polymers that, when placed in water, spontaneously assemble into hollow crystalline nanotubes. What's more, the nanotubes can be tuned to all but have the same diameter of between 5 and 10 nanometers, depending on the length of the polymer chain. Polymers have two chemically distinct blocks that are the same size and shapes. Scientists have learned that these blocks act like molecular tiles that form rings, which stack together to form nanotubes up to 100 nanometers long, all of the same diameter. So nanotubes of this size, and with a self-assembling ability, it's really just a matter of connecting them. You could set up a capillary system to self-assemble inside of anything, really. And then these uniform structures, it changes things. If you can change the diameter, chemical groups exposed in the interior, you can control what goes through it. Yeah, filtration and desalination. In addition, In addition to that, drug delivery. You could wrap very small doses in these, and they only open up under certain, say, circumstances inside the human body, so they only open up once they get to the right place. So I guess this does have potential to have a medical implementation. But it's really more of a materials science kind of deal. Now here is something pretty wild. And would explain our Fermi paradox. So all we've got to do is move the light around, and you can't see the world. How about that, right? So, some Columbia University guys have suggested that we could use lasers to hide the Earth. Prominent scientists include Hawking, cautioned against broadcasting our location, yada, 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 because, well, it's not necessarily a bad idea. And presuming the universe is 13 point whatever billion years old, that's long enough for something else to develop out there. This is assuming, of course, that the universe is not in a stable state and has always been. But that's another discussion for another day. So anyway, a lot of scientists are reasonably concerned that extraterrestrials could be interested in our resources. In an infinite cosmos, you might be too far away from the things you need or might use them up, so come and get them, as it were. Anyway, according to the authors, emitting a continuous 30 megawatt laser for about 10 hours once a year would be enough to illuminate the transit signal, at least of visible light. So basically, we'd be a dark spot, all of the crap in the Jedi Academy thing from that movie. Star Wars. Yeah, of course. Alright, and now we're going to hop into the interesting and kind of frightening world of GMO stuff. So, what we're saying here, they're expecting global populations will grow and urbanize. That will have to produce 87% more of our 4 primary food types: rice, wheat, soy, maize. It's doable. I mean, honestly, using just organic farming techniques and methods and properly utilizing the land, it can be done. I mean, there is plenty. Just look at the food waste in America. There's more than enough for everyone. It's just a matter, really, of properly utilizing the things that are here, that are available, you know. But what this article says, basically, is making a crop more efficient. Not going so much after the Monsanto Franken-crops, just taking what you've got, give it a tweak. Make it grow a little faster, make it grow a little bigger. Make it take in a little bit more carbon. Because, of course, that's the big thing, you know, carbon in the environment, so we want to take it out. That would be an easy way of doing so. And also, you know, you've got the options of making crops more weather resistant, which definitely a win. Now then, the end of days and the beginning of days. So, I don't know if any of you have heard, but this Planet X is apparently a real thing. As we had been told so long ago in so many ancient texts, the planet that came in and left. What they're saying here, though, is that this planet, when it comes and goes, as is reasonable, would bring with it huge meteor showers and comet storms. Which, you know, considering it would go on a kind of a transverse axis to our normal orbit patterns, when it comes to the Kuiper belt, it picks up a lot of debris, and it would shower that down on the face of the Earth. A number of the other planets as well. Now, mind, according to the really basic calculations I've done, we shouldn't see that planet until at the earliest 2300. At the very, very earliest 2100. And this is based on ancient texts, so really couldn't say. But it should be arriving between 2100 and 2500, based on its roughly 10,000 year orbital cycle. So, when it comes through, I'll quit at you. When it comes through, it would just rain down terror on us. But the thing is, we're already working on these, well, how is it said? These are demons we can fight. These are troubles we can conquer. We're already working on mining asteroids. Once we can mine an asteroid, we can destroy an asteroid. And if we can destroy an asteroid within... I see us mining them before the decade's out. So then we should very well be able to reroute or destroy any number of them by 100 years' time minimum. I mean, as long as we don't kill each other, which it looks like we're about to make it over the hump. Relatively safe and relatively unscathed. Then we're going to be going out there. where we belong. That's our birthright, you know. That up there, all of it. It's where we belong. And we need to bring everything along that we can. Well, I'm going to go ahead and cut it at this. That's a number of interesting articles. I hope everyone has enjoyed this little science. 20 minutes. Well, I'm out of here, and we'll come up with some more goodies later. Bye. Oh, hey, if you like what I'm doing, I could really use some help. So, if you can, really be awesome if you checked out my Patreon. Links below. And I'm doing like game giveaways and cool stuff. So, you know, you won't be doing it for nothing. Bye for real this time.